Today's video is on linear approximation, which uses the derivative to estimate the change in a function without actually calculating it. So here's some notes for you. So if we remember the derivative definition, what we're really calculating is the limit as the change in x becomes really small. That gives us the change in the y, the change in the function, over the change in x, essentially the slope. And when x is really small, this part here, when x is very small, is essentially the derivative. So when the change in x is really small, the difference between the f compared to the x is basically approximately equal to the derivative at that point. And we can rearrange this formula so that delta f can be shown to be approximately equal to find the derivative at point A and multiply it by the change in x. And that's essentially linear approximation. Graphically, what we're doing is, here's our axes, and we've got some function. I'll do it in green. We've got some function. Here's a, and here's a plus the change in x. This point would be in the y direction, f of a, and a point up here would be f of a plus delta x up here. The derivative, the tangent slope would look something like this. So this value here is delta x, and this value here, using the derivative, is f prime a times delta x. That's my approximation. Notice that the approximation's off of the real amount by a little tiny bit, and that's because this whole amount here is actually your change in f. But we're pretty close, and that's the basic idea of using the derivative, essentially using the tangent line to approximate what value is close to a value that we already know on a graph. Here's an example of how that works. So we're going to use linear approximation to estimate the difference between a couple of values, and then try and calculate how accurate this estimation is. So we'll apply linear approximation, and we need a function to be working with, and the function is 1 over x. And it's 1 over x because 1 over x nicely models 1 over that value and 1 over that value. So we have some more data. We've got x is 5 in this case, and the change in x is equal to 0.1. So there's your x value, and a little bit bigger, there's your change. Now if we go and grab the formula, now if we compute the exact value, the change in f is exactly whatever the function is worth at 5.1, take away the function worth at 5. That's asking us to calculate this exactly. Take away 1/5. That's the exact answer. Linear approximation is going to find us an answer close to that. So the linear approximation formula is approximately equal to, the change in f is approximately equal to the derivative evaluated at a times the change in x. And our original function was x to the negative 1. And so our derivative function is negative x to the negative 2, and that evaluated at a, and in this case the a value is 5, is negative 1 over 25. So the change in f is approximately negative 1 over 25 times delta x, and delta x is 0.1, and so we get a value of approximately negative 0.04. Now if we grab the calculator and we calculate exactly what it's worth, the change in f is exactly, grab the calculator to do this, and I get a value of negative 0.0039215686, and a bunch more decimal places. And you'll see that our approximation and our exact value aren't off by that much. So, how accurate is this estimation? Well, the difference between both of these tells us how accurate it is. So, our error isn't very much. Our error is approximately, well, it's the difference between 0.0039 to all those other decimal places, take away negative 0.04. I absolute value so that I get the positive error, which is just a magnitude, and I get about 7.8 times 10 to the negative 5, which is really small. It's just a little bit smaller than 1 times 10 to the negative 4. So it's within quite a number of decimal places of accuracy, 4 decimal places of accuracy, which is pretty good. Sometimes linear approximation is written with different notation. That means now instead of the change in x, we're talking about dx, or delta x, and therefore the change in y would be the slope times the change in x, because before I had a formula that was delta f, which is the change in the y direction, is equal to f prime of a times the change in x. So these are very, very similar, just using a slightly different notation. Notice that delta y is, you take your larger y value, and instead of delta x, it's dx, and you subtract away your smaller one. So the change in y is equal to that equation. And the change in y is, as we said, approximately dy. And we can use that to do an example as well. So how much larger is the square root of 49.1 than the square root of 49? And of course, we could just grab a calculator, calculate these two out, and get an exact, or pretty close to an exact answer. But linear approximation takes this and uses functions to approximate those differences. And so let's do that. First of all, applying linear approximation, we need to find a function that shows these two numbers, and the function would be the square root function, which can also be written as x to the 1/2. And we are starting with an a value of 49 and a change in x values of 0.1. So that's our dx. And our dy, using the formula from above, the a plus dx minus f of a, tells us that it would be exactly 49 plus 0.1, take away the square root of 49, which, as I said before, we could do on the calculator and calculate what that is worth. We're going to approximate it. To approximate it, I need to know the derivative, and the derivative of this is 1/2 x to the negative 1/2. And at an a value of 49, that's the same as 1 over 14. And therefore, dy is equal to f prime of a times dx, and f prime of a is 1 over 14, and the dx is 0.1, and I multiply those two things together, and I get a value of about 0.00714. And if I were to compare that to the actual value, I would get a value that isn't too far off of that, and I've got a really, really, really close approximation to that square root, take away the other square root. We can also use the tangent line equation as we did in the past. We could calculate the tangent line equation to find an approximation, and that's called linearization. So if we can come up with a tangent line equation, I'll call it L of x, and what we've seen in the past is that it is the slope times x minus a, the slope evaluated at a, so that's the derivative evaluated at a, times x minus a plus f of a. That's essentially the point slope formula rearranged, and you'll notice that the function is approximately equal to evaluating the line. So if you remember the graph that I showed you earlier, if you found the tangent line and you evaluated it, it was approximately equal to the function. So another way of completing an estimation is to use the tangent line. There's a great example. It's example number 5 in the ebook that you should probably take a walk through. And then you can go and try the pre-class questions for this section.